You know what I'll do? I'll do it at the same time.
Are you talking to me? Somebody was talking, I don't know.
I think he was trying to say what time is the assignment due tomorrow.
Oh, 10, by 10.
Oh, okay.
I have many students who already submitted it. I got it yesterday and today. It's about the quantity discount and the production lot size, 2 questions. And we covered this Monday, Tuesday. Usually students did a very good job in this assignment. As usual, remember, the assignment was really successful, all the assignments beforehand. All what I want to see that you understand the concept. I'm not tricking you on anything here. So it's a good preparation for anything. And the quiz will be, depending on which course do you belong to, on the 20th and the 21st. If I'm not wrong, you know, just look at the syllabus of your course. So 20 or 21st, I think, of April is where the quiz is. I believe at this point it will be about inventory. Probably not the EOQ because we already had it before. So one of the models will be there on the quiz, and what is not will go to the last exam. So that's all about the assignments. Okay. Okay, so did I open the recording? I think I did, yes, okay. The model that I'm about to talk about is EOQ with safety stock. So you see EOQ comes in. Safety stock will come to answer the uncertainty in the demand. The point is that in all your EOQ coverage so far, the safety stock was given. Somebody was determining how much safety stock to hold. But in this model, we will come with a safety stock that will meet a given service level. Service level is a concept that was not used before and is widely used out there when the risk or the chance of getting shortages is becoming really severe. And so you hold safety stock to reduce this chance. Now the question is, how much safety stock to hold in order to reduce the chance to some acceptable level of shortages? So the service level that we are going to apply has two types, and we are going to use only one of these two. One basic concept in this model is the following. For the sake of determining how many units to order in each cycle, you assume in the long term that the demand is constant. Now, well, somebody is talking. Your mics are open, so you have to be careful, guys. So the demand is not known. So what is known is the average demand. You use the average demand for the sake of determining how many units to order. So the EOQ formula, where you have the square root, and then you have 2 times D times the CO divided by CH. D is the known demand under EOQ conditions. In here, you don't know the real annual demand because it's random. So you use the average demand as a replacement, and you say the average demand for the whole year give a good enough presentation of what the real demand per year is. So if you look at a full year, you can say that in this model. So Q star is calculated based on the square root formula of the EOQ. This is the side of how much to order. But the question is when to place the order. When you have demand that does not behave as expected because it's unexpected, it's random, then you cannot wait too long before you place the order if you have a lead time. We include lead time in this model. Because if you wait too long, inventory drops close to the end of the cycle too much, and then the probability of getting shortages is increasing. So you have to prevent that. That's why you have to place a reorder point early enough. And that's the essence of the rest of the discussion. Where is the reorder point? And what is the safety stock? These two questions need to be determined in this model. So as you see, the safety stock is not given. It will be the outcome of a service level. Now, service level that we are going to look at is the one on the left. It's called the cycle service level. Let me tell you what the unit service level is first. The unit service level is looking at how many shortages you expect in each cycle. And you calculate the percentage of the demand that the actual demand that will be filled out from inventory, that is without shortages. And you will predetermine what is the acceptable percentages. So the unit service level is the probability that you can fill in an order from the inventory. The other one is the cycle service level. Here you are not counting how many shortages you have at the end of the cycle. You count how many cycles you have when you had enough inventory. And if you have shortages, so be it. You don't count how many shortages you have. There are many cases in which you don't care how many shortages you have. What you do care that you had enough inventory to meet demand. So in this cycle service level case, we will count the number of cycles in which you meet that you had enough inventory to meet the demand, and we'll calculate the percent of those cycles, and this will be the cycle service level. It's easier to deal with the second one, the cycle service level, than the first one. You don't have all the probabilistic tools, mathematical and probabilistic tools to deal with the unit service level that is harder to obtain results for. But the cycle service level, you have everything, and you will see in what's coming that it's really not hard to do. It's easy, actually. And the results are very interesting and lead to some budgetary conclusions and safety stock holding cost conclusions, and so on. You'll see. That's what we are about to do. Here is a description of how the EOQ model looks. And the demand here is considered known with certainty and constant. But in reality, in this model, it's not like this. The orders are not necessarily of the same size, but the demand goes along the straight line, up and down. At a certain point, the demand dropped to the level of the reorder point. Then you place an order here. The order will be received L time units later. So the demand continues and the order is received here. Now, if you notice, we under EOQ condition did not expect any problem at the end. In reality, we had a shortage. We already ordered Q units. As I said, this Q is the Q star that we did with EOQ. But customers that placed order here and did not receive it waited. And therefore, you start with negative inventory here. Those parts of the demand that were not answered on time. And therefore, from the order here, first you meet this demand, and then the rest you put on shelf for selling later. Notice that the maximum inventory here is lower than this one. That's because we started at negative. A new cycle now is starting. And the cycle now, if you notice here, at the end of the cycle, we expect, based on EOQ, a shortage. But this did not happen in this cycle. Why? Demand started to be smaller. During the lead time, the demand was smaller than expected. So you ended up at the end of the cycle with some inventory here. And the new order has been received, and therefore the new cycle starts with higher inventory than before. As you see, cycles are similar to one another, but they are not identical. And that's the nature of the uncertainty. So this is what we are dealing with in this problem. Some cycles will have shortage, some will not. So this is a summary of what we've just seen. In this cycle here, and it tells you here, lead time demand exceeds reorder point because the lead time demand started from here down to here, right? And the inventory at the beginning of the lead time was the reorder point, and it was only this. So when the lead time demand exceeds the reorder point, you are going to have shortage. In here, the lead time demand does not exceed reorder point. Here is the lead time demand from here down to here, but the reorder point was from here to here. So the demand was smaller, and therefore at the end of the cycle, we had some inventory left over. What we want to achieve is the percentage of cycles that look like the happy face will be large enough. That's the cycle service level. And we convert this percentage into probability. So we want the probability that a cycle will have enough inventory to be large enough. Large enough means equal to the service level predetermined. So the service level that we are interested in developing is the probability that lead time demand does not exceed the reorder point. Notice that we are focusing on the lead time alone, because if anything bad is happening in a cycle, it must be happening in the lead time. Beforehand, you will not have shortages. If anything happening, it will be during the lead time, because that's the end of the cycle when you have low inventories. So therefore, we are going to look at the lead time demand and compare it to the reorder point. The point is that during the lead time, we cannot ignore the uncertainty. We ignored the uncertainty behavior, the uncertain behavior of the demand for the sake of calculating Q star. We are not doing it anymore when it comes to the reorder point, when it comes to the possible shortages. So our job is to find what reorder point will meet the service level that is externally determined by management on us. In order to determine the reorder point, we need to know what is the demand distribution during lead time and what service level is imposed on us. Us meaning the inventory manager. So I decided to work only with a normal distribution for two reasons. First of all, you know how to deal with normal probabilities. Secondly, many times the lead time demand is normally distributed or assumed to be, and the assumptions seem to work well. And so it's not out of the blue distribution that is not used out there, although I have to tell you, it's not the only distribution that is used. Now, in order to find the reorder point based on the information provided to us, we are going to use the function norm inverse in Excel. Okay. The way it is working is this. The reorder point will be the norm inverse function. In Excel, you have to go to Excel and type it. Here you put the service level that is known to you. It has to be known. Here you put the mean during lead time, the mean demand. And here you put the standard deviation of the demand during lead time. This will give you the reorder point. Why? You'll see the graphical description in a minute, so it will be clear. Now, here's a little example. Suppose demand during lead time, normally distributed with a mean of 150, mu L. Standard deviation 35, sigma L. And management want 85% of the cycles to have enough inventory. So they are willing to tolerate 15% of the cycles to not have enough inventory. So the cycle service level is 0.85. To get the reorder point, you use norm inverse, 0.85 service level, 150 mu L, sigma L, and you get 186.2. Now, depending on which type of a product do you have, if this is an unacceptable value, then you may use 187 instead. Don't use 186 because you want to maintain a service level of 85. Then you have to upgrade it. So you round up and you don't round down. So in a case like this, you'll have a reorder point of 187. Okay. If you do, you guarantee that you have at least 85% cycle service level. Now, this will explain this situation with the R. Did you notice that 186.2 is more than 150? Now, think about it. If we have no uncertainty at all, nothing, and we do know that the demand is constant and we know at what level. So we know to calculate the lead time demand. Actually, we use L times D for the EOQ. Suppose we come up with 150. Then you don't have safety stock. You don't have to have safety stock. You know that the demand is constant and your reorder point then will be exactly 150. Now that we do not believe we have a constant demand and we do have uncertainty, our reorder point is 186, so it's higher than 150. I'm showing it to you because here, you see, you place the R somewhere on the right-hand side of mu. And now you have to decide what is its value. Well, this is the demand during lead time here. No shortage is going to occur if this demand is lower than the reorder point. So we can calculate now the probability that the demand will be less than R is the probability that you have no shortage in a cycle. Because if DL does not exceed R, then the probability that DL is less than R should be whatever the management decided the service level should be. So it's in the graph, it's here. But what R guaranteed that you have 85% here? That's the norm inverse. So that's what the norm inverse is giving you. They are above mu that guarantee the service level. And now you can come up with safety stock. Because without uncertainty, you will place your R here. With uncertainty, you place your R here. And the difference between them is a safety stock that prevent the service level to go below 85%. So the safety stock is not something that is coming just because you think so. It's based on some probabilistic calculation. So the safety stock is the reorder point minus the mean demand during lead time. So that's what I told you. This model will determine the reorder point and thus the safety stock. And that's the achievement that this model is giving you. And in this case, the safety stock is 36.27. So you will take a safety stock of 37 if you need to round. Okay. So now I want to work with these numbers to come up with different results. So you'll see a few cases. To the AAC problem that you had before, we had it before in both the EOQ case and the quantity discount case. I'm adding here lead time of 5 working days, okay, which means 1 working week. That's the lead time. And now we have to estimate, remember that we have to know the mu L and the sigma L. Well, we have to then to know what is the mean demand per 5 days and the standard deviation per 5 days. Now, the data in that problem was provided as a table over 10 weeks of weekly demand. And so you could come up with the mean per week of the demand and the standard deviation per week of the demand, okay? Now you have to translate this into mu of L and sigma of L. You immediately see we don't have a problem because the way the data was collected was, and it was weekly, and the lead time is a week. So we have the data ready for us. But I want to give you a more general expression that will make it possible for you to make adjustments when these 2 time units are not the same. We have to determine what mu L and sigma L is if we want to use the norm inverse function. And this is what I was talking about. If the lead time is L, and if the time unit used to collect the data is L prime. Example, you collected data previously every week, which is 5 days. What if the lead time was 10 days? So you don't need the mean per 5 days, you need the mean per 10 days. How do you transform it? The mean per lead time will be the lead time divided by the time unit for the data collection times the mean that you get from the data collection. You see an example, it'll be easier, clearer. And then the sigma, pay attention, the sigma during lead time is the ratio that I used before here, but now you take the square root. Sigma is outside the square root, and you get sigma of L. So now let's look at some numerical example. Determining mu L and sigma L. Let's assume the lead time is 5 days. That's what we had before. The lead time is 5, and the data also were collected along every 5 days. So mu during lead time equals to 5/5, so it's L divided by L prime, times the mean of the 5 days data collection, which is mu of L prime. Sigma of L will be 5/5 square root times the standard deviation of L prime. So this way you find the sigma L and the mu L. Well, it happens to be the same as mu of L prime because the ratio is 1, both here and here. Then what if the lead time was 8 days? Now it's more than a week. I don't need for my norm inverse the mu per week now. Guys, do you know that your mic is open? Can you mute your mic? They will not stop. Hello. Do they hear me? Stop talking. And mute your phone, your mic.
Professor, can you try to mute it?
And I'm recording now. Okay, well. So for a lead time of 8 days, do you hear me? Can you mute your mic? I hear you. Is it Kiaud 1?
Yeah, that was the one that kept talking.
Okay.
She said sorry.
What's wrong with her? Okay. Okay, so the lead time now is 8 days. And now it's more than a week. And therefore, we cannot apply the mu of L prime. We have to make mu L present here. So we use that formula that make the transformation. We have L equal to 8 and L prime equal to 5. Okay, so mu of L will be 8/5 times 120. 120 is the mu of L prime. And 9.12 is the sigma of L prime. So these two give us mu of L and sigma of L. And from here on, we can continue with the task of determining what the reorder point is. Okay, so now let us look at several cases using this information. if the company have been using a reorder point of 130. So notice that here the reorder point is known. What service level the company used to work with? If L is 5, then the reorder point 130 equals to the norm inverse, unknown service level, mu of 5 days, and sigma of 5 days. To find the service level, I'm using now the norm dist function that finds probabilities. So the service level now will be norm dist. R is known to be 130, mu 120, sigma 9.12. Don't forget the word true here at the end. You can also put the number 1 instead. And you'll get 86.33, which is the cycle service level that this company used to have. So the safety stock the company used to hold was 10 units. Why? It's a reorder point minus the mu, it's 10. Different results, you can do it yourself. When you are looking at the PowerPoint yourself, you can practice. Different result you will get if for example, they kept here 125 units reorder point. Of course, the service level then will be lower. Just for practice. Okay. Now, 86% means service level means that 14% of the cycles end up with shortages. So management might decide that this is a little bit too much. And they go to the extreme and say, you know what, tell us what happens to your safety stock if we increase the service level to 99%. Again, 5 days. You know that different results will be if we take 8 days lead time, because then the mu L and the sigma L that goes to the norm inverse are different. So you get different probabilities. So the question is, for here, which safety stock the company needs to hold now for 99% as opposed to 86%, and how much more they are paying on holding cost for holding more safety stock. Obviously, it's going to be more safety stock. The safety stock that they are going to hold is the reorder point minus the mean demand during lead time. The reorder point will be norm inverse, service level of 99 and the rest of the parameters, minus the mu, give you 21 and change. You upgrade it, round it up to 22. And this problem was about selling juicers. So they come in a whole number, so I upgraded to 22. Now, the safety stock holding cost is calculating based on the EOQ approach. You have holding cost per unit per year times the level of the safety stock. So because we have before 10 units of safety stock and now we have 22, so we have 12 units more. So the difference in holding safety stock will be CH. 1.4 comes from 14% that AAC was using per year times $10 per unit. So give you 1.4 CH times the safety stock minus CH times the old safety stock. And this will be how much more they pay for the safety stock. This might be a case in which management might say, you know what, this increase in cost, it's too much. And so maybe we shouldn't go to 99%. But this is a negotiation kind of between the inventory manager and management, or between the operation manager and the accountant. So they have to agree what's best for the company. That's why this information will be provided to management in order to make better decisions. And don't forget, this is not a single item in which they go to 99%. They may have 1,200 items, different items in the warehouse. Each one has its own safety stock and service level. So they upgrade the warehouse service, and this accumulates in costs. So they have to see what they can afford. Now, and this is just another way of expressing the service level, just in case management find it hard to, or find it not intuitive to give you percentages. For management, it's better to count how many cycles a year they have and say, okay, in one of these cycles, I can tolerate a stock out. Stock out means a cycle where you don't have enough inventory. Indeed, in this problem of AAC, there are about 19 cycles a year. How? This is the average demand per year. And this is the order size. If you go back to the EOQ, this is the order size that was calculated as EOQ. So D divided by Q is the number of orders per year. Here it's on the average because the mean demand is not 6240. It's the average of it is 6240. And so 19 is the average number of cycles, of which management can afford one cycle stock out. So therefore, an estimate of the probability of shortages for management is about 5%. But then 18 cycles out of 19 will not have shortage, which is about 95%. So the cycle service level that is coming out of this restriction is about 95%. And sometimes management find it easier to define service level as the number of stockouts per year. Okay, and that's all why I showed it to you. Oh, and once you know this 95% or 95%, then you continue as before. You can determine the reorder point, the safety stock, and everything. Second example. I am here using new values. The only thing that you've seen before was 192, which was the mean demand during 8 days lead time. But I changed the sigma to 35, and I changed CH to 5.5. Both are larger than before. Now, management is allocating a budget. So I want to investigate the relationship between budget given and what service level you can get from this budget and what safety stock you're going to have. So you have the money allocated to holding the safety stock. Management, because they work under budget constraints, that's what they decide to do. They are giving you a budget and now you do the best you can. So what is the service level that can be achieved? This $50 given to you should be equal to CH times SS for holding safety stock. CH is 5.5. Safety stock is to be determined. Safety stock then will be 50 divided by 5.5, which ends up to be a little bit above 9 units. Okay. But you don't have more than $50 for this. So therefore, you cannot round it up. If you round it up, you'll have to use more than $50. Now you have to round it down. Therefore, the safety stock that you will use is 9 units and not 10. So now, what service level can be achieved? If the safety stock is 9, the reorder point is 201. Take a look. R minus mu is 9. R minus 192 is 9. R is 201. So the reorder point will be 201 units. Now we can calculate the service level. Norm dist with all the good stuff from before, and we get, guess what, 60%. With $50 allocated for holding safety stock, you get 60% service level. You run right away to management, say, hey, you know what? That's what you're going to get, 60%. Now they have to check to see if this is acceptable to them or not. If they say, okay, for this juicer, 60% is really, really bad. We have to give you a little bit more money and you can redo the calculation. Now, with the 60% that we already have, we want to estimate what is the penalty for a full year that you are paying. This is a sensitive question because you have to estimate how much you are paying penalty on a stockout. That is, on the average, what's the penalty to you, the manager or the system, for not having enough inventory? And remember here, sometimes you have small number of shortages, sometimes you have large number of shortages. We don't count in this method how many shortages we have. So what we come up with is the average penalty over all the cycles where we have a shortage. And it turned out to be $15. That's just a number that I came up with. No special reason. So how do we estimate the annual shortage cost to us or penalty? And by the way, the penalty is just you, the seller, need to penalize yourself for not having enough inventory. And that's because customers become dissatisfied. You may lose some of them, so you lost business. You may, for the customer who are willing to wait, what you're doing, you are rush in order. For rushed order, you have to pay more. So the difference in cost is a shortage cost. And so therefore, there are penalties for shortages. They are not free. So $15 on the average is what you are paying per cycle, okay? Now, how do you come up with the estimate per year? You have to look at how many cycles you have per year, and of them, how many cycles you have shortage. So how many cycles you have per year we came up with before? It's 1908. Now, the expected number of stockouts is, if the service level is 60%, then 60% of the cycles have enough inventory. Therefore, 40% of them do not have enough inventory. So 1 minus 0.6 times the number of cycles is the number of cycles in which you have stockouts. Each one of them costs you 15. So the annual penalty per year is the annual shortage per year. The cost of the shortage is 15 times the expected number of cycles in which you have a stockout. And this is an estimate of the penalty to you because of shortages. What do you do with this? Well, you can compare it to how much you pay for holding costs of the safety stock. So if the shortage cost under a current safety stock policy is this, and you try to improve the policy by increasing the safety stock, so you pay more for holding cost. See how much you save. See how much you save here on shortage cost. If you save more than what it costs you to increase the safety stock, then it's a good move. So that's what you use these values for, to make a decision about, but now it's based on costs. If you want to increase or decrease the safety stock, you don't want to pay on safety stock too much if you don't save enough on shortages. But this discussion is a little bit beyond the scope of our course, but this is what is done in order to come up with some more informed decision about safety stock. Remember, safety stock might be a very expensive endeavor. For safety stock, if you have many, many items, all of them is safety stock, you need room for that. You need to stock them somewhere. Maybe you have to rent some space nearby and you pay rental monthly. So maybe it becomes too expensive. So you don't want those safety stock. Then you are willing to give up on the service level. This all comes into the equation. And of course, we are not in a position to discuss all this. So this is the cycle service level model that I had in mind. I'll send to you some questions or a problem that demonstrates some of these concepts. And now the question is, do you want to ask questions about it before we move on? Okay. Yeah, let's see if there is. Kiauduan, I accept your apology, but it was long. It was long, and I needed to stop the sharing. That's unfair to others because now the recording will be screwed up, I have to say. Yeah, Audrey, I know, it was annoying. It was annoying, what could I say? I didn't want to mute the student because sometimes students need to ask a question. But okay, that's the price we have to pay sometimes. Now, somebody asked me to show how to use the template, the inventory template for the homework. Oh, it's Audrey. And now, and Hector asked, can I go back for a bit? Let's see. Okay, so first of all, Hector, what do you want me to go back to? You can tell me.
Oh, it's okay. I wanted to check something that was on one of the slides, but I could check the recording later. No worries.
Okay, good. Thank you. And that's why I'm sending the PowerPoint to you guys. And actually, you know, when you use the video, you can stop it and go back. And the video will have the PowerPoint. So I hope this is good enough. Yeah. And now, Audrey, you want me to show how to use the template for the homework. I did it already yesterday and the day before. I showed the template, how to use it for the production and how to use it for the quantity discount. I can't do it now. But the good news is you have the PowerPoint already and you have the recording there from yesterday. Just go online, go to Dropbox, and you can go over the presentation until you hit the template, which will be at the end of the presentation on the quantity discount. I have a slide on the template, and at the end of the production lot size, I have a slide on the template of these two templates. So that's what I can tell you now. I can't really go and do it now. Yeah, the homework can be done in groups. Like, I don't make any changes. To be honest, Eliza Otero, no one so far has done it in groups. I don't want to make it hard on you. It's an assignment. I want you to study from that. If you want to do it in groups, do it in groups, fine. I think it's a better idea to do it yourself. So if you do it in group, also do it on your own first. And if you want to compare it with someone, good. But then tell me who, are the people there, because I don't want to miss anyone. Okay. For the assignment, I guess. Well, tomorrow I get all the assignments. I already am grading, but I want to send to the whole class in one email. So I'll wait till everyone is turning it to the full class. I'm already am grading. I am telling you the grades are really great. And I'm yet to find someone who got less than 85. So if you're doing it on your own, you're doing a nice job. I have to tell you that. Well, that's what I saw among those who already turned it in. So yeah, you want to do it with someone else, go ahead and do it with someone else. But in my opinion, you are missing your own challenge here. And it's not challenging. It's regular questions like you see in the text that I sent to you, like you see in the examples in the PowerPoint, same kind of questions. Okay. So, and thank you, Audrey. Listen, after you look at that, Audrey, after you look at the file on your own, please email to me if you have a question, okay? Because you should not have a question. It's very clear there. But if you have a question about the template, it's a shame to not know how the template works. It's designed to help you. So I don't want this to happen. If you do have a problem with the template, don't hesitate to email to me, okay? Thank you. Okay, so now I'm going to linear programming, and let me ask you a question before I go. I might need 5 minutes of your time beyond the 75 minutes, something like that, because I want to start something and stop at a point where it makes sense. Anybody has to leave? Just, you can say, I have to leave or something. So you're all going to stay with me, right? Okay, thank you. So that's what I'll do today. I'll start linear programming. I'll tell you what it is. I'll show to you an example, simple prototype type example, okay? And at a certain point, I'll stop and continue from that point on Monday, Tuesday, and next week, okay? So I'm going to share again. Just a moment. Generally speaking, linear programming is a branch in a larger area called optimization. By and large, in an optimization problem, you try to find the best course of action to go under given restrictions. And linear programming is doing the same, but all the functions that you will be using are linear in nature, make it much easier to set up and easier to solve. It's nothing to do with programming, no computer programming, no language, so it's misleading. It's just a traditional name given to this area. It's a very popular field in business because it can help management making better decisions in any area that you may think of, production, finding the best production plan, in management, finding the best recruitment plan, in finance, finding the best portfolio, in marketing, finding the best advertisement campaign. So it's very popular. It's used a lot for planning of the short run and long run in many companies. I'm starting here with a very small problem, intentionally small, from production. I can show to you what does it mean using graphical approach, but bear in mind, it is only good for a small problem like the one I'm showing to you. I'm using this in order to explain what does it mean to solve a linear programming problem. So the company called Galaxy is a manufacturer for children toys. Among others, they have two types of dolls. One is called the Space Race, and one is called the Zapper for games in space. They have a production problem here. They realize that two of the main resources that they have are limited. They have 1,000 pounds of special plastic that they use in the production of both, and they have 40 hours production time that has to be dedicated to produce both combined. So whatever production plan they will come with cannot use more than what is indicated on the screen here. Sitting and trying to plan for next week, they realize there are other restrictions. The total production cannot exceed 700 units combined. The units come in dozens because that's how the production line is designed to work. And in addition, and by the way, this might be a marketing requirement, but it can also be an operational requirement. Marketing, because the marketing manager might say, you know what, don't stuff the market because it might drop our prices. Keep the market starving a little bit. So he wants to limit it to 700. Or it can be the operation manager who might come and say, you know what, next week, I'm planning to stop the line on Thursday night because I have to go over maintenance and the line will not be working. So we have to limit our production to 700 dozens combined. Okay. The number of dozens of space rays cannot exceed those of zappers by more than 350. That's a marketing requirement. Why would space rays exceed zappers at all? Because later in the next slide, you'll see that space rays are more profitable. So the tendency in the company currently is to produce more of those and less of the zappers. The marketing manager is afraid that if there will be no limit of 350, the niche in the market for zappers will drop for competition. He wants to protect it. Then he says, you know what? The difference between space rays and zapper cannot exceed 350. So I'm giving you just a possible scenario where those restrictions come from. In order to formulate the model, you have to know how much plastic and how much production time is needed per unit of each product. So space rays require 2 pounds of plastic and 3 minutes of production time. The zappers, they require less amount of plastic, but more time. This information is needed in order to set up our linear programming model. So what's the question here? The question would be how to organize our production plan for next week. What would lead the thinking is the profit. So you make $8 per dozen for space rays, and you make $5 per dozen on zappers. As I said, space rays are more profitable. So now the question is, how many of each unit to produce in order to maximize our profit? What does the current production plan consist of? 450 dozens of space rays and 100 of zappers. You see the difference is exactly 350. You see that the sum of them is 550. That's less than 700 as required. We can check to see how much plastic we use for this plan and how much production time we are using for this plan. And in both cases, we don't violate any of the availability of those resources. And we can check to see how much money we make. It's $4,100. You see how it is calculated? See? 8 times 450, 5 times 100. And now management is thinking, wait a minute, is it the best we can do? The reason they think that it might not be the best is when calculating how much production time is used for this, you don't use all the 40 hours. Some hours are unused. Plastic, you use it all. But time, production time, not. So management think maybe if we reorganize our production, we will utilize our resources better. Maybe then, not guaranteed, we'll make more money. So that's what the linear programming is designed to do. To find a production plan that maximizes the profit. And how do I know I need to maximize profit here? Maybe minimize cost. It's another objective. No. In this problem, the data given was profit. And therefore, that's what I try to achieve, maximize the profit. Okay, so let's see. We are going to set up now a linear programming model. You start by defining two decision variables, because here you have two. One, the production level of the space rays and of the zappers. I call them X1 and X2 for convenience. And X1 is how many dozens of space rays, X2, how many dozens of zappers we are going to produce. This is what the model should tell me later on, such that my profit is maximized. So because this is my objective, the second element after the decision variables is called the objective function. At the top of every linear programming model, you have an objective function. Objective function is either maximized, normally profit, or minimize, normally cost. But I have to tell you, there are problems in which it's neither profit nor cost. Sometimes you want to recruit police officers to because some people got fired, some left the service. You need to recruit people and you want to minimize the number of police officers that you recruit such that you can meet all the requirements for your shifts. Because each police officer costs money, so you don't try to minimize cost, you try to minimize the number of recruits. Each story in each problem is different. You read the problem and you set up your variables, and then comes the objective function. In our case, the objective function is this. So, that's the objective function. Now, 8 times x1 is the profit for producing and selling x1 dozens of space rays, because 8 is the profit per dozen. So is for 5x2. The sum is giving you the total profit. You write the value max here to indicate for yourself you are maximizing here and not minimizing. But this maximization has to work under a given set of requirements, restrictions, resources, marketing restrictions. They are called, in linear programming, they are called constraints. So you subject yourself to. First constraint, plastic. Here is the plastic constraint. This is a typical linear programming constraint. 2 times x1 is the amount of plastic that you use in producing x1 dozens of space rays. 2 is the pounds. How many pounds per dozen you need to produce such dolls? And 1 times x2 is the amount of plastic that you are using in producing x2 dozens of zappers. The sum is the amount of plastic that you are using in your production plan. This cannot exceed the amount available. So that's why it's less than or equal to 1,000. Okay? Then comes a similar constraint on the second resource. Now we are talking the 40 hours available. On the left-hand side here, you have the amount of time that you use in order to produce your production plan. 3 and 4 are the minutes needed to produce each dozen of space rays and zappers respectively. And 2400s, now you cannot write 40 here because this is coming in minutes. So you have to convert the 40 to minutes, 40 hours times 60, 2400 minutes. That's the production time constraint. And now comes the third constraint. Total production combined cannot exceed 700. You have X1 dozens and X2 dozens of the two products, cannot exceed 700. And now come the last constraint about the difference between space rays and zappers that cannot exceed 350. You see, X1 minus X2 cannot exceed 350. There is one more non-negativity constraint that is more mathematical that appears in all the linear programming problems that you will see, that is needed just to tell you that you don't have negative values of X1 and X2. And also because the software that we are going to use next week does not allow negative values. So you can add it, and if you forget, I'll forgive you. It's not resulting from the information given to you in the problem, but those constraints are the result of the information as you read it. And you know what, in this book, oh, I forgot to tell you, chapter 12 is the chapter that covers linear programming. We are going back to our textbook. And the text is well written. So you will see the problems at the end of chapter are really organized such that almost every sentence is a constraint. If you read carefully, you will see we are trying to help you understanding the constraint this way. But it's just critical reading, not critical, comprehend your text, comprehend your reading. That's how you'll know how to set up your model. And this is a linear programming model. And for each problem, you'll have a different model. But for each problem, you'll have to come up with the decision variables and then use them for the objective function and the constraints. How do you know which decision variables to come up with? Usually it will be, think of yourself as the manager here and decide and ask yourself, what do I need to decide? In terms of operation, what do I need to decide here? I need to decide how many products or units to produce from each product. Okay, so now we have a linear programming model, and now you ask them, okay, what do I do? Why did I set it up? You set it up this way because this will lead to the solution, and the solution will include how many units to produce of each variable and what will be the maximum profit. And that's what I want to finish with. First of all, you will form what is called a feasible region. This is on the plane of X1 and X2, the region where you should look for the optimal production plan. The word optimal means the one that maximizes the profit. You will use a graphical presentation because this is what I'm using in order to demonstrate the concept of linear programming. We are not going to go a lot of graphical solutions at all because nobody is doing it. It's only good when you have two variables. Once you have more than two variables, you cannot use this method. So I'm only using it as an instructional tool to demonstrate the concept of linear programming. X1 represents space rays, X2 represent zapper. Do you understand that if I had three products that compete the same resources, I would not be able to draw it here? I would not be able to get a solution. So this method is very limited to only two variables. No problem in the world, in the real world, has only two variables. They have 22, 52, and this is even small. So of course, we are not going to use this method. we have a software that solves it. It's called Solver. It's in Excel. You already have it, and we'll talk about it next week. So in here, I'm using this in order for you to see what does it mean to optimize a solution. First of all, x1 is not negative and x2 is not negative. Somewhere here, you'll find a combination of x1 and x2 that maximize the profit. But not every point here is feasible because there are constraints to meet. The plastic constraint is this one, for example. 2x1 plus x2 equal to 1,000 is this line. You see, it's a straight line because this constraint is linear. So for a straight line, all what you need is to find 2 points on the line and take a ruler and combine it and connect them. Well, it's very easy to find 2 points on this line. Put x1 equal to 0, x2 will then be equal to 1,000. x2 equal to 1,000 is 1 point of the line. Took x2 equal to 0, take x2 equal to 0, x1 equals to 500, and you have this point. Take a ruler, connect them, and you have this constraint. Just a moment. Nobody bothers me now. Okay. So this line represents a production plan or production plans, many combinations in which exactly 1,000 pounds of plastic are going to be used. And this is feasible because you have it available. I'm not saying it's optimal. I'm just saying it's allowed. But you don't have to use 1,000 pounds if you don't want to. You see, it allows also to be less than, not necessarily equal to. So where is the less than area? In here or in here? All what you need is to find 1 point in one of these sides, calculate how much plastic is used, and see if it meets the constraint or not. If it does, then it's feasible, then that side of the line is feasible. The best thing and easiest thing to do is to plug in 0 and 0 here as if you produce nothing. I'm not saying it's optimal, I'm saying, is it feasible? How much plastic you use? 0 pounds. 0 is feasible because it's less than 1,000. So this point here is feasible. It's under the line, so the points under the line here are feasible and those are infeasible. So I color them with different colors, you see? Now I know that I can't use the whole plane, I have to use only this triangle to look for the optimal production plan. But it's not enough, I have more constraints that I have to meet. For example, the production time looks like this. And I'm using the same kind of considerations to find how the line behaves. And again, it's less than or equal to, similarly to the previous constraint. So I have to be under this line. And if I have to be under this line to be feasible, this part here is infeasible. For the second constraint, I color it, see? Now the feasible region became smaller. But this one meet both constraints. So I have a third constraint. That's the total production of 700. See? Now, this constraint is a straight line with between 700 here and 700 here. This constraint I colored with white and not blue because it's a different kind of constraint. It's called redundant. This constraint does nothing to what you already know is feasible. Why is it so? Because the line here goes above the closest point, which is the corner here. It's above. You want to be under the white line because look at the constraint, it's less than or equal to 700. So you need to be below it, but you are already below it. The green is already below it. And so if you leave it or take it, you don't change the current feasible region, so it's redundant. If it's redundant, I don't even have to consider it at this point. Later in our discussion next week, we will have to go back to this constraint. And then comes the last constraint on the difference between the two products of 350. And this constraint goes up and not as the other two that went down. And why is it so? Take a look at the constraint here. If x1 is 0, x2 is negative 350. Do you follow? Negative 350. So it will be somewhere here below. And if x2 is 0, x1 is positive 350. So this is 350 here. So the line goes from this point all the way up, and I show it only in the feasible part of it. Now the line is less than or equal to 350. Where is it? Above the line or below the line? Try the point 0 and 0. You see, I always go to the easiest that is easy that I can calculate, and I see that 0 and 0, when you look at the constraint, is less than 350. So it's feasible. Therefore, to be above the line is feasible here. So I color this one, and now I have the feasible region. These two are the non-negativity, and now you have the production time, and you have the plastic, and you have the difference. All those define the feasible region, and now you know that whatever you do, the production plan must come from within this green area. So if you take one in the middle, it will have that many space rays and that many zappers. And you know it's feasible. I'm not saying it's optimal. Now we ask, how do we maximize the profit from within this area? Okay. And that's the last part, guys. I hope nobody left. In order to find maximum profit, you have to use the profit function. We haven't used it yet. I'm going to draw the profit function at some profit level, arbitrary profit level. I don't care which level you take. So I selected 2000 because I wanted to cut inside the feasible region and I want it to be easily drawn. So it's easy to draw this line, and this is how it looks. What is this? 8 times x1 plus 5 times x2, the profit function, is equal to 2000 on this green line. Now, is $2,000 the highest possible profit? Well, if you can't find a better line that is feasible, then this is maximum profit. But if you can draw another line that has a larger profit and it's cut inside here, then this one cannot be optimal. Indeed, as you start increasing the value 2000 here to larger and larger values, you see that the line, you see what happens. The line is moving up. That's how the profit increases. So it's moving away from the origin. So you want it to move further and further in the feasible region until you can't increase it anymore. Each line that you draw to the right-hand side has a larger profit. That's what happens here. This red dot is your optimal production plan. If you try to take the green light higher profit, you go outside the feasible region into the infeasible region. So therefore, it cannot be optimal if it's infeasible. So it turns out that this point here is the optimal production plan, and it turns out that 320 dozens of space rays and 360 dozens of zappers give you the largest profit of 4360. You see how it is calculated? Under these conditions, you cannot get a higher profit than this. This is what it means to solve a linear programming problem. So how did you find 320 and 360? Well, a bold method will be just read it from the graph. There is an algebraic method that gives you the exact solutions, exact solution. But I don't care about that. We are not going to read solutions from a graphical approach. I'm only using it for you to understand how the optimal solution is obtained, and pay attention to this point. It's called extreme point because it's sticking out. In the feasible region, it is sticking out. We have most extreme points. Here, this one is extreme point, and this one is an extreme point, an extreme, an extreme. So the feasible region is built on extreme points connected by constraints. And we will pay attention to these later on. So the optimal solution was found, and next week we will take problems that are more than 2 variables. Forget about this graphical approach, and we will learn how to use Solver, the software, to solve such a problem. And all the solutions that you will be getting will occur at extreme points of those problems of next week. So that's what I want you to see today for the linear programming. Okay, so what happens now? Okay, let me just stop the sharing for a second. And what I do now, I work on some exercises that I want to send to you, not on linear programming yet. It's too early, but I want you, if you can, go to chapter 12 and read a few pages at the beginning, introduction on linear programming, what it is, and look at the example there. There is a prototype example that's similar to this production problem that we have. Cover this example. They are talking about the graphical approach also. Read that. It will give you a very good foundation for what's upcoming. Then he shows the computer-based solver solution. You may not go to that. As far as solving problems, if you feel comfortable, there are like 3 problems, I think. Whenever you see a problem with 2 variables, try to do it with a graphical approach for your own practice. Solutions for those appear on the website. For chapter 12, you have solution for that, for all the problems in the book, but I don't think it might be too early to try to do more advanced questions. Let us talk about it first of all between the 2 of us, and then you'll have enough time to practice. So that's all for linear programming, okay? Any questions that you want to ask now? Are we good? You want to talk? You want to say? I'm listening. Okay, so if things seem to be clear, this and the previous inventory model, then I'm working on sending to you some review on this inventory first. I put this as a priority first. And you also have some problems that I think I sent to you some problems to practice for all the inventory models. I'll give you a new additional problems from the text I sent to you of problems that you may want to look at for the service level. They have like 2 problems there. So I'll take a look and send you an email with what I think it's a good idea to do at home. And with this, I can say thank you for coming. Okay? Any comment? Any? Yeah, thank you for sure, but what else? So it was clear, both things were clear today. I need to know, really, I want to know. Anybody want? Yes, no, that's all. Oh, okay. Somebody is asking what will be part on the quiz? What do you mean? What will be included in the quiz? You mean? I think for the quiz will be only inventory. Now I don't know which model yet. It can be any of the three that you have. It can be the quantity discount. It can be the production. It can be the cycle service level. But one of those will be on the quiz. And I'll tell you, we have time for that. Another thing that I think I do next week, I'll try to set up some office hour. It's kind of funny. I think, yeah, I'll try to do it maybe before class, or I didn't decide yet, but maybe one time in the morning and one time afternoon, twice a week. For those who work in the morning, they will have a chance to come and do it afternoon. So I have to see exactly when I'm available for these office hours. And so next week we'll do it. And in an office hour, I'll just be sitting with you and I will not present anything, okay? I will let you ask questions and see if I can answer them. So that's for next week. And we have time before the quiz. Okay, so that's all what I wanted. If there is no other question, then I say bye-bye. Okay. No template for the quiz? No, I didn't say no template for the quiz. Why not?
I just wanted to know if we were going to be able to use the template for the quiz and for the exam.
And if I say no, if you use it, would I know?
I won't use it if you say so.
Yeah, of course. Listen, I'm not limiting you, sir. As long as you understand what you're doing, and if I'm asking you to explain and you can, then the template is just there to help you. Why would I not agree to that?
All right, thank you.
No, of course not. Okay, so bye-bye.